Hello everyone, you're all welcome. Uh, I'm Deniz Can Yılmaz. I'm a senior at Middle East Technical University Computer Engineering Department, and I also work as a software developer. And today I'll talk about the Internet Computer blockchain. My presentation will be consisting of mainly two parts. In the first part, uh, it will be more about the theoretical part of the Internet Computer. I'll be talking about what its key components are, what its architecture is like, and what its most useful uh, use cases are. And then in the second part, it will be more on the practical side of the ICP, and I'll be showing you some smart contract examples to give you an insight of how we can develop on it. So I'm going to start off with the definition of Internet Computer, what it actually is. The Internet Computer Protocol, ICP, is developed by the Definity Foundation. It was released in 2021. Its revolutionary blockchain infrastructure seeks to expand the functionality of the public internet. It aspires to be a scalable, open, and secure world computer. And the main aim of the Internet Computer is actually to provide a cloud computing platform that runs on blockchain that can run any Web2 application on fully on chain. It allows Web3 applications services to run fully on chain, and smart contracts, and we call canisters. We call them canisters on the ICP, and they serve web pages. It hosts programs and data as smart contracts, known as canisters, on a network of subnets, and each subnet runs on node machines. Each canister has its own isolated data storage, and they communicate seamlessly with other canisters across the network. The ICP runs at the core of the network and ensures fault tolerance and scalability. The reverse guest model enables free-to-use, truly user-friendly dApps. It enhances the user experience immensely, and I'll be talking to you about it in a few seconds as well. The architecture of the Internet Computer. For the architecture, I'll be mostly talking about four key components: canisters, nodes and subnets, chain key cryptography, and nervous network system. Smart contracts on the ICP are called canister smart contracts or canisters. Each canister consists of a bundle of WebAssembly bytecode and smart contract data storage. Canisters are autonomous, scalable, and interactable software units. Canisters are computational units that bundle together code and state. They expose endpoints, which can be called both by other canisters and by parties external to the Internet Computer. So even though Internet Computer is fully on-chain, you can interact with a backend canister from your JavaScript frontend, which is deployed on a Web2 service. The code of the canisters is single-threaded, and they're executed in complete isolation of other canisters. Canisters can be immutable, unilaterally mutable, and deomutable. By immutable, we mean that it cannot be mutable once it's deployed. Unilaterally mutable canisters can be altered by the developer of the dApp, and deomutable canisters can be developed by a DAO. So a DAO is authorized to make changes on the canister. Inter-canister communication. The Internet Computer's multi-subnet architecture allows canisters on different subnets to communicate with each other. It's actually very similar to the microservices architecture on Web2 services, but it's fully on-chain. Canisters communicate via asynchronous messages, allowing the Internet Computer to scale by adding more subnets. HTTPS outcalls. Normally, blockchains provide smart contracts with access to external data via oracle bridges. But on the Internet Computer, we have HTTPS outcalls by a default property. So there's no need for oracle bridges because canisters can communicate with external APIs, and they fetch data from external resources by making HTTP requests. So on other blockchains, first an off-chain authority reads from data source and writes to a dedicated smart contract, and then other smart contracts read this data with requests to this contract. And there are some downsides of it, and I'll be talking about them in a few slides. But on the Internet Computer, we have direct HTTPS requests, so we can retrieve data without any intermediary parties involved. So oracles on other blockchains introduce several risks, such as centralization, data manipulation, since there is an external party, dependency and single point of failure, because the execution of our code depends on an outer source again. It can be costly because the data is written on another smart contract and there are transaction fees involved in this case. Trust and security, these are the several risks they introduce, Oracle breaches introduce. Reverse gas fee. I mentioned about the reverse gas fee in the beginning of my presentation. On other blockchains, each user pays a certain fee, not certain actually, a volatile fee for their transactions on the blockchain network. But on the internet computer, we have a reverse gas fee model. So the developer of the D app pays for the transaction fee beforehand, and it is applicable because the transaction fees on the internet computer are uh, a lot cheaper compared to other blockchain networks. As you can see here, there are gas fees for every time something needs to be written to the blockchain, and they are variable, volatile, and they are unpredictable. But on the internet computer, there's reverse gas fee model, and it is free for the users, just like Web2, and no fee is paid by the user. So it enhances the user experience immensely. So it actually offers a user experience similar to the Web2 applications that we have today. It's a great feature for, you know, mass adoption of the Web3 applications on the internet computer blockchain. The reverse gas fee model is also called compute capacity power, and computation and storage costs are paid for by the developers. Developers burn ICPs and receive cycles, which is the unit of computational cost on ICP. And they're all paid beforehand, so there is no need for the user to pay any gas fee for their actions on the blockchain network. The second pillar of the architecture of the internet computer is nodes and subnets. Canisters are hosted on subnets. A subnet is an independent blockchain running on node machines, which are deployed in globally distributed data centers. Subnets are responsible for processing transactions and executing smart contracts within their own subnetwork, and they can communicate with other subnets, enabling the internet computer to scale horizontally and support an unlimited number of applications and users. There are mainly two types of subnets. System subnets are reserved for canisters that are an integral part of the internet computer. For example, our network nervous system runs on system subnets, but application subnets are default subnets that users can deploy their canisters. So your DApp is actually your DApp canisters can actually run on application subnets. These are the two basic types of subnets, but there are also specialized types of subnets that offer certain additional properties that might be useful to the apps. Nodes are the individual machines that make up the internet computer, and they are deployed in globally distributed data centers. Nodes can be run by anyone, and they are incentivized to participate in the network through rewards in the form of ICP tokens. So our canisters are deployed on subnets, and our subnets work on node machines. Traditional blockchains are limited by the computing power of a single node machine because every node has to run everything that happens on the blockchain to participate in the consensus algorithm. Running multiple independent subnets in parallel allows the internet computer to break through this single machine barrier. No single entity has the power to significantly disrupt the network. The principle in the regular blockchain networks that as I mentioned, actually was challenged in the Hetzner incident, which is in the Ethereum network. Hetzner, a popular hosting service, banned Ethereum nodes, and this action effectively removed a substantial portion of Ethereum's network nodes, leading to concerns about network stability and decentralization. Since our nodes are distributed, this is not likely to occur on the Internet Computer blockchain. And the third pillar of the architecture is chain key cryptography. It's actually what enables internet computer to work at web speed. It allows the internet computer to achieve functionalities and scalability that are impossible on other blockchain networks. The chain key technology is a 48-byte public chain key that renders all blocks unnecessary, which enables the internet computer to operate at web speed. And it also enables the internet computer to scale to millions of nodes. So on other blockchain networks, when a transaction has to be processed, all nodes on the chain should verify it. But on the internet computer, thanks to the chain key cryptography, only a 48-byte public chain key should be processed. So it is actually what makes it so fast. Anyone can verify the content received from the internet computer by simply validating a signature without syncing the entire blockchain, as I said. The topology of IC can evolve autonomously. New nodes and subnets can be added, faulty nodes can be recovered, and protocol can be upgraded autonomously. And canisters can secure their own algorithms that need randomness. This technology divides the execution of smart contracts functions into two types, and I'll be actually showing them on the second part of the presentation, where I will analyze some smart contracts. But the two types of functions are first update calls and second query calls. Update calls make some changes on the chain, so they execute relatively slower compared to query calls, and they run in 1 to 2 seconds. But query calls run in milliseconds. To validate an outcome of a smart contract on Ethereum, an open Ethereum client needs to download 400 gigabytes. To make matters worse, the required download size only grows linearly with time as more blocks are added. But on the internet computer, this is not the case. And this is an illustration of the architecture of the internet computer. As you can see, our canisters run on subnets, and subnets run on multiple nodes. Chain key cryptography, as I talked just before, ensures the addition and deletion of new nodes. And internet identity, and I will be covering that as well, is used for authentication purposes. And this final pillar, the fourth pillar of the architecture, is network nervous system. NNS is responsible for the governance and management of subnets within the Internet Computer blockchain. It works on system subnets, and it's actually a DAO. The NNS manages the creation and deletion of subnets, as well as the allocation of resources and management of subnet upgrades. Each individual DApp on the IC can have its own governance system, similar to the NNS, by customizing and deploying an out-of-the-box tokenized DAO, and this is called SNS, and I'll be covering that as well in the use cases of ICP part. The core IC protocol, it runs at the core of each subnet and ensures fault tolerance and scalability. It has four layers: peer-to-peer layer, consensus layer, message routing layer, and execution layer. Peer-to-peer layer ensures secure communication between nodes within a subnet. Consensus layer runs the consensus mechanism, which is a threshold relay on the ICP. Message routing, it handles the routing of messages between canisters. An execution layer executes canister smart contracts. Executes canister smart contract codes using a WebAssembly virtual machine on each node. Several use cases. I have actually talked about some of them. Internet identity, direct Bitcoin integration, SNS, and 100% on-chain applications. Internet identity, it's a decentralized identity system on the ICP blockchain. Normally, we can use wallets to authenticate on and authorize on blockchain networks, but in ICP also supports it, but we also have something unique, which is called internet identity. It enables users to manage their own digital identity and authenticate without passwords or centralized powers. It is based on public key cryptography. Users control their own data and selectively share with the apps or other users. It helps you create and manage anonymous, independent accounts for every website. So a website cannot track your other actions, other activity on the blockchain. As I said, this prevents websites from collecting and sharing information about your online activity and presence. Direct Bitcoin integration, it's a new feature. Internet computer allows canisters to hold and transfer Bitcoin without the need of any intermediary layer or bridge. It allows you to send Bitcoin quickly and fee-free by using chain key Bitcoin, which is a Bitcoin clone on ICP. Since ICP smart contracts can perform transactions on the Bitcoin network, they now allow developers to develop applications on Bitcoin as well. Service network system. SNS, as I mentioned in the nervous network system part, is a type of DAO as well, but it mainly works for applications, DApps. It allows developers to fully decentralize their applications and fund their applications by selling governance tokens, which is ICP in our case. And so far, applications have received a total investment of $15 million through SNS DAOs. 100% on-chain applications. The main goal of Internet Computer was to publish fully on-chain apps, and we have several examples of it now. The ICP is actually emerges as a rival to central cloud providers such as AWS, Azure, and Google Cloud, and is actually a cloud computing platform that runs on blockchain. It can host applications that require high computing and storage capacity, such as social media and messaging platforms. And thanks to its unique reverse gas fee model, which we have covered, it is possible for users to use the Internet Computer applications without interacting with any cryptocurrency. So here are some examples of the applications that we have on ICP. OpenChat is a chat application similar to Telegram. Discover is a social media platform similar to Reddit on Web2, and District is like the ICP version of Twitter or X. And here is a link to the developer grants program if you're interested. So this was the end of my first part of the presentation. I covered the architecture of ICP, several use cases of it, and I've given you some theoretical information about what Internet Computer really is. So on the second part, I'll be talking about development on Internet Computer. So there are several concepts that I want to explain before showing you some code. The concepts are DFX, Candid, IC, Rust CDK, and Motoku, and I'll be mentioning them now. DFX is a command line interface that is actively developed by the Definity Foundation. It allows developers to create and test smart contracts in their local environment. It also helps build and distribute large-scale applications on the Internet Computer, and this is actually why most of our commands start with DFX, like DFX start, DFX deploy, etc. Candid is a interface description language, and its primary purpose is to describe the public interface of a service. It's language agnostic, so whether we develop with Rust or Motoku, we can still have our Candid UI. It enables us to interact with our smart contracts, our endpoints, without the need of implementing the front end. And it's actually pretty cool for testing purposes. And I'll be showing you some examples of Candid UI as well as we deploy our smart contracts on our local machines in a few minutes. IC Rust CDK. IC SDK supports Rust programming language as well as Motoku. To create a Rust project, all you need to do is add the type equals Rust flag while creating a new project. And this is a link to how you can install it. All these are present on the internetcomputer.org webpage. IC actually supports, Internet Computer actually supports several languages such as Motoku, Rust, Python, and TypeScript. There are several CDKs, canister development kits for those purposes, but mainly Motoku and Rust are used for development purposes on large-scale projects, and there are and the documentation is richer compared to other languages and CDKs. So several crates are provided on the IC Rust CDK. to achieve the functionalities of the Motoko language. Uh, as I've said, Motoko is the native language for development on the internet computer. It's a great engineering investment by the Definitive Foundation to come up with and create a new language for their blockchain network. And there are some functionalities of it that are not available in other languages. So we have some crates here, Rust crates, that enables us to achieve those functionalities. ICCDK, IC stable structures, ICCDK macros, and ICCDK timers. ICCDK is the core library. It comes with default, but we have to add IC stable structures and ICCDK timers manually. IC stable structures provide us with some data structures that we can write our data to and keep our data organized. ICCDK timers is used for heartbeat functions, which are similar to cron jobs on Web2 applications, but on Web3. And it updates, and we can create some timers and interact with them similar to cron jobs. Yeah. So how can we create a new application? For example, if we want to create an application with Rust, we use this command, dfx-new --type equals Rust, and the name of our project. And we have a project structure like this. Most of our code is in the source folder. Here we have our backend and frontend folders, subfolders. And the backend folder, cargo.toml is used for our dependency management. Example backend.dit file here is used for configuring our candid interface, and lib.rs file is actually the file where we make the development. And we can also configure any JavaScript framework or library for our frontend, and for this we have to configure this webpack.config.js file, and then we can start using the we can start implementing our frontend in the example frontend folder here. So this is the URL to the sample project that I will be using today. So I'll be switching to it now. And this is our project that I've implemented. It's a basic to-do application to do on chain. At first, I will import some crates here. I have candid. From the candid crate, I import candid type, decode, deserialize, encode, and principal. And I'll be explaining them as we use them later in our code. From the ICCDK, I use caller function, query update macros, and API time. This is used for interacting with when we want to get the system time, because we cannot simply use the chrono crate of Rust on the internet computer from the IC SDK. From IC stable structures, I import first some macros and definitions related to memory manager, and then bounded storable, default memory implementation, stable B-tree map, stable send, and storable. And these are coming from the STD standard crate of Rust. And then here I implemented new type, memory type here, and I'll be using them in my memory management, virtual memory implementation here. So okay, first I define my structs that I want to, how I want to keep my data. My first struct is to do item, and here I have some fields. Caller is of principal type, and principal is simply who is calling the function and an identity of the caller of the function, and it is taken automatically by calling the caller function here. And then I have an ID of type unsigned integer of 64 bits. And then I have an assigning of type string, a description of type string, a duration of type 64-bit unsigned integer, an isActive field of type boolean. Updated and created at are kept as timestamps of 64 bits of unsigned integers as well. And this is what I'm going to save on my memory location, stable B-tree map. And this is also the second struct is to do item view struct, and this is this only has four fields, because update and create that ID, etc., they're all going to be generated on the backend here. There's no need for users to provide that kind of information here. And here I have the derive macro on my before my struct definitions. I define them as deserializable because I'll be saving them on stable memory, and they're also going to be candidate type. This is because on my candidate file I'll also define those structs here to specify the inputs and outputs on my functions. So after defining my structs, I have an enum here, and this is actually for error handling. I'm specifying several types of errors here, and for logging purposes actually. I'm also defining them as candidate type because I'll be returning them in some of my endpoints. And then I'll be defining storable for to-do item because I'll be storing them. These are, you can think of them as boilerplate code. And then I have a bounded storable implemented for to-do item here. Bounded storable trait implemented for to-do item here. I'm going to limit them. I'm going to specify an upper bound here because I want them to be a maximum of 500 bytes here. And then I'm going to specify them as not fixed size because they are not going to be a fixed size because I have some fields like string fields here, and string fields are not of fixed size. They're going to shrink and expand. And now here comes my memory implementation part. Normally, in a memory location, we can only keep one stable structure, but in order to implement several stable structures, which are stable B3 map and stable cell, in my case, as I've imported here them, I'm going to implement a virtual memory. So I'm implementing my virtual memory here, and in the 0th index of my memory, virtual memory, I'll be implementing a stable B3 map, and it will keep the keys as unsigned integers of 64 bits, and the values are to-do item structs. And I'm implementing them here in the 0th index of my virtual memory. In the 1st index of my virtual memory, I'm going to keep an ID counter. Actually, you can generate a random ID, but I wanted to implement it here this way, implement a counter on my virtual memory this way, because I wanted to show how we can keep more than one stable structures on a virtual memory at once. And here, similar to the to-do map implementation above, I'm implementing my ID counter here as a type of stable cell. So after defining my structs and implementing my bounded storables, storable traits and bounded storable traits, and implementing my virtual memory, now I can implement my endpoints and helper functions here. I will first implement a helper function. It simply interacts with the ID counter, takes the current counter, and takes the current counter and returns its value. And before returning it, increments it because it has to be it has to be maintained that way, because we don't want two items to have the same kind of ID. And my first endpoint is fetch all. Here is a function. It takes nothing, and it returns a vector of to-do items here, wrapped as a sum enum. It interacts with the to-do map virtual memory portion, and takes all values here and pushes them on a vector and returns it. And here I also implement this as a query function because I'm not making any changes to the blockchain. I'm just taking data from it. So I'm specifying it as query here, and I'm defining its name as fetchall because on my candidate file, I'm going to interact with it as fetchall. And get function, it's also a query function because it does not make any changes, doesn't alter the blockchain, and it again interacts with to-do map, takes the item with the given key and returns it. And now comes my update function here. It's an update call. its name is create. It is used for creating a new. It's used for creating a new item. It takes to do item view of type of data and then returns a to do item wrapped in with an option. I first take the ID that I'm going to create, and now I'm going to create a new to do item. As you can see here, those fields are coming from the to do item view, and others are created here. I'm using the time function here that I import from the API module of ICCDK, and other than that, after creating my to-do item here, new to-do here, I'll be interacting with to-do map and inserting it. Before inserting, I check if the given key is existing. It's not possible, but it's again a check against if anything occurs, and then I'm going to insert it. And in my second function is update function. Here I have is authorized flag actually, because we don't want a user to update a to-do item that they're not authorized to alter. And then I have my return item here. It takes a key, a value, and then returns a result of message in case of both success and failure, error and success. So it again interacts with to-do map, virtual memory portion, and it takes all to-dos and searches for the given key, and then again creates a new return item, a new item, which we will insert if they're authorized. If the authorized flag is false, then it will return an error, not authorized error, and otherwise, if our return item is filled with some data, it will return it and save it. It will actually save it on the to-do map and update it, update the given key. Otherwise, it will return an error, no such item, because we have not found an item here in the red to-do variable. And our last function is delete function, delete endpoint. Delete to-do function is implemented here. It first finds the to-do item that is wanted to be deleted, and then if an item is found, it first check if our caller is authorized, if the caller ID, if the principal on the found to do is equal to our caller, and if it's not, it returns error, no authorized error. Otherwise, it deletes the item and returns success message. If nothing is found, again, then it returns no such item error. So this is basically our smart contract, a simple to-do app implemented on ICP. And now, since it's all implemented, I'm going to analyze the candidate file here. And the candidate file, as I said, I have a messages variant. This is an enum, so I use the variant keyword here. And this is my type, record type, to-do item, and to-do item view, actually, similar to the here, my structs that I've defined here. And I'm going to define them as types here, record or variant types. And my responses, since they are wrapped within some, they are going to be either OK or error messages, and they will be of type messages, either of these three options. So after defining my types, I implement my source. I define my services. Fetch all, as you can see here, this is the name of my query call. Fetch all does not take any arguments and returns a vector of to-do item type wrapped in a sum option, and it is a query call. I only have to specify the query calls here, and get, create, update, and delete are also implemented, corresponding to my function definitions here. So now I can deploy it on my local replica actually. Before that, I have to start my VFX. For that, I'm going to use VFX start dash background dash clean. And now my VFX is starting a local replica. And now I deploy my smart contract as the FX deploy. As you can see here, it creates both a front-end canister and a back-end canister, because both of our front-end and back-end are kept on the Internet Computer blockchain. And since I have not implemented in the front end now, I will not be uh, visiting this URL, but in order to interact with my candid UI, I'll be using the backend canister URL. I'm going to click on it, and it's now going to be opened. And this is my candid UI. Here you can see my function names, what they take as arguments and what they return. So first, I'm going to create a new to-do item. Assign is Linus, duration is specifying in days, for example, 10 days. Description is test is active, true. I'm going to call my endpoint here. And if I now fetch all items, here I can see my record here with the ID 0. If I create another one here with the test2 description, here you can see it will have a ID of 1. Yeah, ID of 1. And I can update my update anything, any item with by specifying their ID. I'm going to change duration to 5, description to test is active to false, for example. Now it returns success. And now if I fetch all my endpoints here, the duration is changed to 5 years, and it's not active, as you can see here. And here it takes my principal by calling the caller function on my backend canister. I don't have to provide anything. The timestamp as well is taken by default on my backend. I can also delete any to-do item here, like this. It returns success, and now I only have the record with ID 1. So this is how we can develop a basic smart contract on the Internet Computer using the Rust CDK Canister Development Kit. And returning back to my slide, um, yeah. And now I'll be talking about the Motoko language. Motoko is the native language for programming on the Internet Computer. It has some specialized features for building decentralized applications on smart contracts on ICP. And in order to achieve its functionalities, we have several crates and libraries for other canister development kits, as we saw in the Rust CDK. Motoko is a statically typed language, and it implements the actor model for asynchronous communication and concurrent operations. This allows canisters to communicate with each other effectively on the Internet Computer blockchain. And now I'll be showing you a basic smart contract on ICP using the Motoko language. But for development on Motoko, you don't actually have to, if you're not working on a large-scale project, you don't have to set up a developer environment, because we have something called Motoko Playground, where you can create smart contracts and deploy them seamlessly without paying any gas fee again on the Internet Computer blockchain. For example, here are some predefined projects. For example, here is the superheroes project, and I'm going to choose it. And here the project is loaded up here. And this is an instance of a Motoko smart contract, Motoko canister. Here the name of my actor, my canister is superheroes. I'm importing several data types here from the Motoko base library. And I am specifying some types here. Superhero ID of type unsigned integer of 32 bits. It's specified as not 32. And actually, I didn't mention that, but here I also, on the candid UI, as you can see here, I specified numeric data as not net 64 and net 32, etc. they're all coming from the Motoko language. For example, instead of string, I use text because on Motoko, I also specify them as text here. So the second type I define here is superhero type, which has a field of name and superpowers, which is a list of strings. And now I define my stable variables. My stable variables are what I have on what I have in my memory section here. Actually, it is more convenient on the Motoko language because, you know, as we've said, it's a specialized language for development on the internet computer, so it's a lot cleaner. So I'm specifying my stable memory here. First a counter called next, and then a superheroes tree, which is similar to a hash map actually. It keeps them as key value pairs as well. I'm creating an empty tree here. And then I implement my endpoints here, my controllers. The create controller simply takes the current ID, increments it one, increments the ID stable memory with one, then inserts a new superhero on my tree, on my superheroes data type stable memory. And the second function is a query function. I only specify query functions. It's a read. Its name is read. It takes a superhero ID and uh, returns data in my superheroes stable memory, and returns it. Finds and returns the item at the given ID. An update function is similar to create function, but um, it simply finds the item in the given ID, then alters it and pushes it back here in the replace method. And my delete function is simply removing it from the from my superheroes stable memory portion. So this was actually all. And as I've said, we can deploy it without you know, connecting our wallet, etc. From the Motoko playground because the gas fee is paid beforehand. So I'm deploying it now. It will ask for some configurations. I'm going to leave them as default, and I'm going to install it now. It is compiling it to a version bytecode and deploying it on the internet computer blockchain network. Its canister ID is returned here. And now it's deployed. And we can interact with it from Candid UI here. Its Candid UI is also opened here. It's actually very nice. And again, we can interact with our smart contract as we did in the previous smart contract for Trust. So that was all. Thanks for listening, and I hope it was helpful. If you have any questions, you can contact me. I guess my Telegram account will be shared with you as well. Again, thanks for your attention and thanks for listening. See you later.